Okay, so I'm back again. We're going to start, this video starts chapter 23. Chapter 23, I will begin this week, probably maybe late on Wednesday or possibly as late as after the quiz on Friday. And we'll do a practice problem set on chapter 23, chapter 24 together. This will be the last problem set. These 4 chapters will be the ones on the first exam. So chapter 21, 22, 23, and 24 will be on exam 1. So the name of this chapter is Gauss's Law. And this, we're going to start to feel like we're getting really, really far away from any kind of physical thing that makes any sense at all or that you have any interest in understanding too. So I just want to preface that the reason we're doing this chapter this semester is we're trying to get the electric field. We want to calculate the electric field because we need the electric field to be able to say what the electric force is on a charged particle. So we're trying to figure out ways that we can use these bizarre rules of electromagnetism so that we can get the electric field at some point. And if we know the electric field at some point, then we can say, well, the electric field times the charged particle. So the electric field times whatever charged particle I put at that point, that tells me the electric force. And that will tell me one of the forces that may be acting on my object. Maybe the only force, but certainly a force. And I can't tell what my charge is going to do if I don't know what the electric field is, if I don't know what the force is. So that's why we're doing this. That said, this chapter introduces a new physical parameter called electric flux. So far we have electric force, we have electric field. Now we're going to have electric flux. Electric flux is actually this thing. It's a capital phi. Not little phi, which is usually an angle. This is a capital phi. It's different from, so little phi is this, and capital phi gets the big lines that go up and through it. And it is technically the integral of the electric field, which is a vector, dotted with a dA vector, where A is an area. And that at least leads us to what kind of units it should have. It's going to have units of electric field, which is newtons per coulomb, times units of area, which is meters squared. So the units of electric flux doesn't have its own special unit. Well, maybe it does, actually, but I'm not going to use it. I just went way past that. I'm not going to do a special unit for this. I'm just going to say newtons per coulomb times a meter squared. Electric flux is the electric flux actually through a surface. So it's called electric flux, but it's really electric flux through a surface. It is a scalar. It doesn't have a direction, although it can be positive or negative. So the other thing that we've had that was a dot product of 2 vectors was work, way back in chapter 7 and 8 of the book. And work could be negative and work could be positive, right? So scalars can be negative and positive, and that can tell you something about the scalar, about the physical parameter. But they're not vectors. The negative doesn't mean a direction. It just means some sort of negative quantity or positive quantity. So inside this integral, we have this dot product. It's a vector dot product from way back in chapter 3. And it's a dot product of the electric field vector, which hopefully we feel like we have some understanding of. And then this weird dA vector. So it's both the thing we're integrating over, and it's a vector in the sense that it has some direction. So the dA vector has a magnitude, which is essentially just some small surface area like this. And then the direction is perpendicular to the surface. Remember that we're talking about this is the electric flux through some surface. And so the surface has some surface area, of which dA is a small little bit of it, right? So this whole thing has a surface area, right? This whole thing, this is all the surface area of this thing. Here's a little bit of the surface area. And then at each point, there's a little dA vector which points out perpendicular to the actual surface area, the plane of the surface area, is what we say. And this idea of having a surface area and having that be a vector, and the direction of the vector is actually perpendicular to the area itself, right? The area is down here, and then this is actually coming out along the normal to the surface. We're going to do that a lot this semester. So we have a dot product. Dot products from back in chapter 3. If I had vector A and vector B, if I did a vector dot product, it would be the magnitude of A times the magnitude of B times the cosine of the angle that's between the two vectors. Which means that if the angle between them is 0 or 180, then I get a maximum magnitude for my dot product. But if the angle is 90 between these two things, then I've got two vectors which are essentially perpendicular to each other, and I get 0 as the object. So remember that the cosine of 90 is 0. So if A is perpendicular to B, then A dot B is 0. And so if we had this written instead in our unit vector notation, we also could say that it was just the x components times each other plus the y components times each other plus the z components. The only thing that survives a dot product are the parts that are actually parallel or anti-parallel. If we have E dot dA, what we end up with is, again, the magnitudes of these times the cosine of the angle between them. And so an electric flux through a surface is, although we write it like this, it's usually really more like this, and even then things are going to probably simplify out a little bit. If our electric field is constant or uniform and it passes through some surface such that the theta is actually constant between, in other words, the angle between the electric field and the area vector is always some constant number, then everything can come out. The E and the cosine of theta can come out. And then the integral of dA is just the area. How much area? What's the surface area of this thing? And again, this is the surface area, which is pretty much how much is it going through. By convention, if you have electric field which seems to be inward piercing, the electric flux should be negative. If it's outward piercing and the flux is going out your surface, then we say it's positive. So let's try to do an example so that we can actually see something. So number 1 is one of the first ones I have you do. And we have this square surface, and it measures 3.2 millimeters on each side. And so the area here, right, is just the 3.2 millimeters squared. I should probably really write that in meters, so it's really 0.0032 meters squared. That's the actual area. And I've got it immersed in a uniform electric field of magnitude, and so we have this 1800 newtons per coulomb, and it's directed inward, right? It's directing inward, and so we have an inward piercing electric flux. So I'd expect my flux to be negative. And then it tells me this angle, right, is 35. But if I really draw this, so if this is my plane right here, and so here's the normal that they're showing me right there. And that is the direction of the area vector. And then the electric field is actually being directed like this. So it tells me this is 35 degrees. But here's my electric field. So the angle between the electric field and the area vector is actually this one. This is my theta. So that's 180 minus 35 degrees. So my theta is 180 minus 35, or 145 degrees. And so when I look at my flux here, I'm going to have the integral of the electric field times dA. Well, the electric field is constant. It's just 1800 newtons per coulomb. The angle is also constant. Cosine of 145 degrees. And then the integral of just dA is just going to give me the area itself. So I'm going to end up with 1800 newtons per coulomb times the cosine of 145 times 0.0032 meters squared. Let me calculate that. Okay, so when I went through and I did that, I got that I did get a negative, which is what's going to come out of that cosine of 145. 1.5 times 10 to the negative 2 Newton meter squared per coulomb. So that's the flux through this surface. So the more electric, the stronger the electric field is, the larger the flux will be, the larger the area. If this was a bigger surface area, I'd have more flux. It's basically, flux is trying to tell you how much stuff is going through your area. If you have a bigger area, you get a bigger flux. If you have more stuff moving through it, in this case the electric field, you have a larger flux. If you have a better angle, if it's closer to 90, you have more flux. Yeah, so flux is this, and I agree, it's not the most obvious physical parameter that exists. So Gauss's law, this is actually the name of this chapter, says that the net electric flux through a closed surface is equal to the net charge, which is inside of this closed surface, divided by this constant epsilon naught, which is what we've talked about epsilon naught before, back in probably the first chapter. So epsilon naught is just the permittivity of free space. It has this super fun unit right there. So a closed surface, what they mean here by closed surface and net electric flux. So up here, I just had one sheet of surface, one thing, but it's not necessarily, it's not closed, right? There's nothing that separates really the top from the bottom except for on the sides. But you could have a closed surface, which means that you'd have some volume which is inside, which is separated from the volume which is outside. Like say we had a ball or a cube, and there's no holes, there's no windows, there's no open spaces. So we have an inside volume and we have an outside space. And so a closed surface means that it completely encloses a volume inside. And this does not necessarily actually have to have any physical substance at that location. It just is could be just a theoretical Gaussian surface is what we call this, but it is a completely closed off surface. And again, we'll write this again. Written in math, Gauss's law, says that the net flux, so again, this is a little different than the first thing. We didn't have net written on it. Now we have net flux. And instead of just having this inside our integral, we also have the integral written with this weird funky circle here. That tells me this is a closed integral. It's a closed surface. In this case, because I have an A, I can also have closed line integrals, which are written like sort of like this, where you say closed, and then instead of having an dA for saying you have an area, you have a dL, which tells you it's like a closed loop integral, which we will probably also get to eventually this chapter, or this semester, not this chapter. So this is just another way of writing the net electric flux. So net electric flux says net electric flux is written, the actual symbol looks like this. It's electric flux with a net. And then to get a net electric flux, instead of just saying integral EdA, we actually have to put that closed loop sign on the integral, where we say this is a closed surface. Oh, goodness. I just made that go away. This is a closed surface. Now, the other side of Gauss's law, which is actually the Gauss's law part, says that this is equal to the net electric flux through a closed surface is equal to the charge which is enclosed inside, right? You have an inside and an outside. There's some charge which is inside over this constant epsilon naught. So again, Q enclosed here is the net charged inside our closed surface. So let's just think a little bit about this idea of net flux and a closed surface when it comes to something like a cube. A cube clearly has an inside and an outside, and there's a surface area of this cube. And there's actually sort of the net flux should be the flux that comes out, which is positive, right? If coming out is positive, minus the flux that goes in, and that tells me the net flux. Since there are 6 sides to this, I would actually, if I was doing this type of problem, technically I would need to turn this into 6 different integrals. And so my net flux would be the flux that goes through the top, the flux that goes through the bottom, the flux that goes through the left side of the cube, the flux that goes through the right side of the cube, the flux that goes through the front of the cube, and the flux that goes through the back. This is the net flux. There's 6 sides, there's 6 ways for electric field to go in and out. And so we would need to do that. Now, each of these area vectors on the 6 sides are in very specific dimensions, right? If I look at the top here, here's dA. It's sticking straight up in the z direction. And so I can write that dA, the top, is just the amount of dA times k hat. Whereas at the bottom, here's the bottom sides dA. It's also the amount of dA, but now it's pointing negative k hat. Similarly for the left and the right, but now these are in j hat directions, and then the front and the back. So the front is positive I hat and the back is negative I hat. Now remember, when we're doing vector dot products, only like terms, I hat times j, with I hat, j hat with j hat, k hat with k hat, actually survive this multiplication process. And so when we go through, if we have our electric field written in unit vector notation, and they start to get dotted with these different sides, only the ones, so EX will only survive when it deals with the front and the back, because they have I hats. EY will only be for the left and the right, because they have j hat, and EZ will only be for the top and the bottom, because they have k hat. if you think about an electric field, say we had an electric field which was moving straight up and down through here. So say my electric field was moving up like this. Well, that electric field is going to be perpendicular to this side and to this side. It'll also be perpendicular to everything here. There's not any flux going through this side then. The only flux is actually moving up through the bottom and then out the top, right? The flux on the front and back and left and right is 0 if you have an electric field moving straight up and down here. So that's another way of thinking about it in a very physical way. So what we end up with is, in fact, sort of this equation where the top, assuming that these are our directions of our dimensions, where x is coming towards us, y is over here, and then z is up, then we end up with this sort of dimensions. And I'm going to come back and use this equation in the next video for when I do number 9.